I'm Steve White, W4SNW. And one of the best aspects of ham radio is enjoying DX, those long distance contacts, and going through the QSL cards that we exchanged. As hams, we know a little bit about what makes that possible. It has something to do with the sun and that 11-year sunspot cycle. And we know that when the sun goes down, some of the frequencies, some of the bands like 20 meters are going to fade out, and then you have to go lower to 40 or 80 to continue to work any kind of distance. I wondered why. So I did research, I looked into it, literally and figuratively looking deeper into the subject. And I prepared a little presentation called The Prodigal Sun, How the Sun Makes DX Possible. I hope you enjoy it.
The Prodigal Sun, How the Sun Makes DX Possible, presented to the Sarasota Emergency Radio Club on April 3rd, 2023. Stars have life cycles. The Orion Nebula on the left, taken recently at a meeting of the Suncoast Stargazers in Sarasota, Florida, took this great picture of the nebula. These are star nurseries. This is where the dust and the clouds eventually come together through gravity and form a new star. We look back in history. This nebula is 1,344 light years away, basically putting it around the year 679 AD. That's when it started its journey. On the right, the Crab Nebula, the first one actually ever identified with telescopes, is about 6,500 light years away, around the year 1477. This one went supernova around 1054, turned into a neutron star, which is a very densely packed star. Sometimes they form about black holes. But this is where the elements, which we'll talk about in a moment, that form inside stars, get basically shot out into the universe to eventually form new stars. Now, all stars and gas giant planets form from the gas and dust in these nebula that gravity again pulls together and creates pressure and more heat at its core. Now, the stars reach critical mass to start what's called nuclear fusion. We'll talk about that more in a moment. While the gas giant planets such as Jupiter, they never grow large enough to ignite. They don't make varsity on Team Planet. They're only second string, and they would never become stars. Rock planets such as the Earth, they form from heavier elements such as iron, carbon, oxygen, nitrogen. And again, these are created from ejected material in the supernova. Only the large stars can create these heavier elements in any quantity. Now, these elements and molecules also form rocky asteroids and the ice-carrying comets that gravity pulls together and crash into the growing young planets. Indeed, that's where most scientists think our oceans came from these comets. Let's talk a little bit about what's called heliophysics, called Sun 101. It's the study of the sun, and of course, other stars as well. Now, our sun's about 4.5 billion years old, and it's classified as a yellow dwarf star. It's a hot, glowing ball, mostly of hydrogen and helium, and it's the center of our solar system, and it's about 93 million miles away from Earth. Now, it will run out of fuel in about 5 billion years, and that's going to collapse into a red dwarf star. But I think we have a little bit time left. It's about just under 900,000 miles in diameter. It's only an average star in terms of its size. Stars up to 100 times larger have been found, and many solar systems have more than one star. Now, I mentioned that larger stars can produce other elements. Now, we've probably all seen this periodic table from maybe high school physics or in college, and you can basically see how different types of stars can form different kinds of elements. And really, I'll talk about what makes one element different from another, but one of the critical ones is called that atomic number. And You see oxygen has an atomic number of 8, and it keeps going up as more and more protons essentially get formed within the nucleus of these atoms by the forces of stars. Now, Carl Sagan, a brilliant astrophysicist and educator, this quote has always resonated with me: the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. Incredible concept, also very true. So, when you take that multivitamin in the morning and you look in the ingredients and you see niacin, iodine, magnesium, zinc, copper, all those different things that sound a lot like elements, they are. So if you're staying healthy with vitamins and your food, you can thank your lucky stars. Talk of some of the pioneers. Kuhn is a French physicist, and he kind of figured out the force of electrical charges. And there's a ratio proportional to the product of the charges, inversely proportional basically to the distance. And the standard unit of measure of electric charge is shown here, and it's called the Kuhn in honor of his early discoveries. The hydrogen atom is the starting point. It has a single proton in the nucleus and one electron. Electrons form kind of clouds. They don't really orbit like planets around the sun. But the atom hydrogen is about 75% of what's called the baryonic or the elementary subatomic particle mass in the universe. It's pretty much the basic building block of all matter and ultimately of all life. Now, two other scientists, Arthur Eddington, he proposed that stars obtain their energy from nuclear fusion of hydrogen to form the next atom in the chain called helium, and also raised the possibility that heavier elements are produced in stars. And the process, Hans Bethe finally figured out that it's a proton-proton chain reaction. That's essentially the first mechanism. In the larger, more massive stars, there's a second one involving carbon, nitrogen, and oxygen. But it's the proton-proton cycle that in our sun is most important. Now, it took an awful lot of mathematics to figure this out. And let's go through some of the math. Well, maybe not that math. Let's try something a little more basic. E equals mc squared. Again, little high school physics, Albert Einstein. Energy equals mass times the speed of light squared. Now, the mechanism essentially goes through a couple different steps. So you take two protons with this fusion, the heavy heat and pressure inside the star to form a deuterium or a dual nucleus, one proton plus one neutron, and does some other steps to it. But what's amazing is even our little medium-sized star forms about 600 million tons of hydrogen nuclei into helium and converts 400 million tons of matter into energy. That's about 385 trillion joules of energy for those that may be familiar with that unit of measure. But in simpler terms, it's equivalent to the energy released in the explosion of almost 92 billion megatons of TNT per second. So why doesn't the sun explode? Well, it's because there's the hydrostatic equilibrium. It's life's most important feedback loop. For the majority of the life of a star, the gravitational force due to the incredible mass of the star and the gas pressure due to the energy generated in the core of that star balance. And the star is said to be in hydrostatic equilibrium. It's finely tuned and it's actually rather self-regulating. If the rate of energy generation in the core slows down, Gravity wins over, pressure builds up, the star begins to contract. This contraction increases the temperature and the pressure, which leads to higher energy generation rates and a return to equilibrium. Essentially, the energy created starts pushing back out towards the surface. Now, time doesn't really permit to go through what when we were growing up, the atom was the smallest unit of anything in the universe, but they later discovered that there were quarks and they have cutesy names, ups, downs, charms. But what's important to this discussion is the four forces of nature: the strong force, the weak force, the electromagnetic force, and gravity. Now, the strong force is actually the strongest, but it only operates within that nucleus of the atom. You know, opposites attract and like charges repel. So if you have multiple protons, why don't they just push each other apart? It's the strong force that keeps them together. Now, the weak force, on the other hand, has a very interesting property, and it has some intermediate steps. And what that does is it can change a proton to an electron to a proton. So as you have more and more pressure, electrons become protons, the atomic number goes basically up, and you have a new element along that basically table that we showed earlier. As you get further away, the electromagnetic force becomes more dominant, and of course, gravity at the larger scales. Let's talk about the structure of the sun for a moment. There's a core, as there is on Earth, and this is where those thermal nuclear reactions take place. Then once you have this mostly gamma X-ray type radiation formed by the essentially the fusion of matter, it takes literally like 170,000 years to go through that first layer, that radiative zone of the sun. I've seen estimates of 1 million years to get all the way to the surface. You have a tachocline, which is kind of a thermocline by analogy, like you might see in the ocean, where different temperatures. And it's a system kind of between that radiative zone and the convection zone. The convection zone is, as you know, heat rises, cool, drops. Well, it's that process, and it creates a phalanx, if you will, for all these particles, and they get beat up. And so it takes a long time of the heating and the cooling cycle to work their way to the surface. The chromosphere is that relatively thin layer, which causes that magnetic field lines, and that's what's important down the road for our propagation. And essentially, it's what keeps the electrically charged solar plasma kind of together. And you've all seen pictures, and we'll see some in a moment, of prominences that form and extend far into the corona, sometimes ejecting material away from the sun. The corona is ionized elements. Again, an ion is an element that either has lost an electron or gained an electron. It's not the classic balance between the two with the number of protons. And that's the solar atmosphere. And it's, again, mostly in the X-ray extreme ultraviolet wavelengths. You have streamers that form from these magnetic lines, and they can come around. They can extend many millions of miles into space. So let's talk about our sunspot cycle, our 11-year friend that is starting to peak again. And its solar maximum in a couple years, it corresponds with polar flips of the sun's magnetic field. It's not exactly 11 years. It can be plus or minus a few years, but that's on average what it happens. So a complete cycle would be basically 22 years. Sunspots, eruptions called solar flares, coronal mass ejections are common at solar maximum. Now, they call our solar cycle 25 since they started measuring it. It started around December 2019, and it'll probably peak around July of 2025, according to estimates. So here's some great pictures. You can see some solar flares and these mass coronal mass ejections. And we know that this can both help and hurt radio propagation. By the way, the more sunspots you have, it tends to reduce the mass coronal ejections that interfere with HF communication. So here's our friend, the electromagnetic spectrum. And we're all familiar with this. It starts at the very low frequencies, goes through the broadcast band, or various radio bands, up through radar and microwaves. Then it gets to visible light. Now, this is where the astronomers and the ham radio operators have a lot in common, because we basically use different parts of the electromagnetic spectrum. But as you get higher, you get into the ultraviolet, X-ray, gamma rays, and these are the wavelengths that ultimately will make their trip to Earth. So here you see a representation. It's a little over 8 minutes to make the trip from the sun to the Earth. And of course, we have a magnetic field that also protects us. That's why ozone layers are so important. And this is essentially when the process starts for HF. Let's talk about our atmosphere. We start at the lower levels, the troposphere, goes up through the stratosphere. You can see planes and weather balloons, to the mesosphere, and eventually the thermosphere, and you're basically into space. Now you notice there's something missing, and there's a reason for that. The ionosphere. Now it's not a distinct layer like the others. It's a series of regions and parts of the mesosphere and thermosphere where that high energy radiation from the sun has literally knocked electrons loose from their parent atoms and molecules. Again, that's what causes an ion. And these electrically charged atoms and molecules essentially endow the region with some great properties that make our life a lot of fun. And you can see it goes from about 90, or rather around 30 miles up to maybe as high as 600. It grows and shrinks based on the solar conditions, and then subdivides into other regions based on the wavelength of the solar radiation that's absorbed. And we'll see a graph of that in a second. But it's a critical link in that chain that's basically what we rely on. So here's a day-night differentiation between the ionosphere. We have D regions, E, and two F regions, and at night it becomes just an F. And we all know that after sunset, maybe 20 meters drops out, maximum usable frequency, radio signals go into space, they don't reflect back. But it looks like it's a switch. It's not a toggle switch by any stretch of the imagination. And we can see that. First of all, here's the gray line map. Some of you may have clocks that kind of show where sunlight and dark are. And it seems to imply that everything sort of changes instantly. But in Australia, they have this great interactive map that shows how dynamic the upper atmosphere and the ionosphere are. It's always in flux. And same thing with the other chart on the right. This is where our QSB, our band fading, comes from. It's there 1 second, it's gone the next, it may come back. It's because we're dealing with magnetic fields, ionized areas of the atmosphere, all of which interact with radio signals. But I highly recommend, if you check out those URLs there, you'll find these, when you put them into real-time motion, they're quite beautiful and quite fascinating. So we have our solar flux index. It's a gauge of how many solar particles and magnetic fields reach our atmosphere. So that's the first step. And the higher the number, the better HF propagation will be. And it also varies by band. So this index is, between basically 10 and 20 meters. These are the upper HF bands before you get into VHF. And there's a scale, and you can see as the number goes up, conditions will improve. And you just note some of those numbers for a moment. Again, there's some great links here with a lot of explanation and more detail than I could possibly go through today. Now, you may have heard NOAA has A and K values. It's a little confusing. The K index is a code. It's related to the maximum fluctuations of basically what's called horizontal components. They use a magnetometer. It's relative to a quiet day through 3-hour intervals. And there's multiple observatories around the world. And essentially, there's the variation and fluctuation, and essentially it becomes a historic rate of occurrence at around the same time at all observations. So essentially, it's a snapshot. The A index is calculated for the individual magnetometer stations. That value is calculated as the average of 8 3-hour station basically indices observed during a 24-hour day and provides a single average value to indicate the activity level for that day. So it's a little more accurate, if you will. And it was invented because there was a need to derive some kind of daily average for geometric activity, and because the K value is really nonlinear with the fluctuation. So it really wasn't meaningful just to take the average of a set of K indices. And it can be converted back. So essentially, the daily A index is merely the average of a bunch of these smaller 8 3-hour A indices. So again, it's a numerical system. So you have that average reading of the geometric activity. So a lower A index means better conditions for propagation. Again, there's a range. And you can see, depending on what those numbers are, you'll get the best conditions on those upper HF bands 10 to, down to 20 meters. And when the between 1 and 5, those lower readings also are the best conditions for 30, 40, 80, and 160 meters, the lower HF bands. And just to simplify how to find these things out, by the way, this is a chart that shows some of these A index and see how they're presented for those who would like to take a look and get a little more information. This is basically for sites where they're showing the K indices for reference as well as the A indices. So Tad Cook, K7RA out of Seattle, does a good summary, and you can, if you subscribe to the ARRL letter at the end of all the current news of amateur radio, you will see his solar update. And now that you know a little more about it, you can kind of cross-reference and see what the sunspot numbers are in the solar flux and A index and get a pretty good sense of where things are going. Again, there's a URL to get to that ARRL letter. I highly recommend it. Let's shift gears a bit. Two other great forms of RF propagation. Now, I came from Philadelphia. Up there, occasionally the Aurora was strong ionized. You could point your 6-meter beam north. You get a very raspy sideband, but it was great. You work DX off the ionized areas of the Aurora Borealis. And of course, there's also the southern lights, the Aurora Australia. Meteor scatter. I had a good friend of mine, brilliant engineer, passed away about a year or so ago. He liked to do meteor scatter. And that's essentially when a meteor comes in, it ionizes the atmosphere for short periods of time locally. And using high-speed computer generated and copied CW, you can make contacts off the tail of a meteor coming into the atmosphere. Now that's basically all sun-related or essentially coming out from space. And there's another form of propagation that we all know and love if we do anything with VHF, UHF, and on our repeaters. It's tropospheric or tropoducting. This is different. And this occurs essentially when there's a temperature inversion at a height of between, say, 500 meters, 1,500 meters, about 1,640 feet to about 5,000 feet. It can go higher. This is not caused by the local weather or the terrain as much by climatic conditions, frontal boundaries that come in. So when a temperature inversion occurs, the colder air, which usually would sink, gets trapped above the warmer air that usually will rise, and sometimes it gets sandwiched in there. And depending on the thickness of that layer, thinner layers only propagate like microwave. Thicker layers can be used into lower frequencies like our VHF band. Cool, damp air is denser than warm, dry air, hence the higher index of refraction. And the air is normally warmer near the ground and cooler as the altitude increases, but that's where the inversions can come in. So here's a nice graph. You can see that on the left, the cold air is inverted underneath the warm air, and on the right, it's sandwiched in. And what happens is the radio waves act kind of by analogy like a fiber optic cable or an RF waveguide. So it keeps reflecting or refracting the radio waves back and forth, and it can go very long distances. And that's when you want to get your grid squares and work a lot of new states on 6 meters, maybe 2 meters. That's when the FM broadcast stations come in from 150 miles away, or when you hear another repeater on the air and you can't quite figure out why they can't hear you. And with that, I hope that was informative and you enjoyed it. And thank you very much. If you have any comments, please feel free to contact me at Whiskey 4 Sierra November Whiskey at ARRL.net. I'm Steve White, and thank you very much.